So, good afternoon, my dear students. My name is Dr. K.C.H. Apparao, working as an associate professor in mechanical engineering department. So, in previous class, we discussed the heat transfer between two plates. So, in this class, we'll see the heat transfer between two plates if we place any shield between the two plates. So, it means heat transfer with shield or shield 1 or 2 or maybe you will see. Okay. So, last class we already discussed the basic formula. So, which is Q net between the radiation heat transfer between the two surfaces. So, here we know this one. So, Q net is equal to sigma into area A1, you can write like this one, T1 to the power of 4 minus T2 to the power of 4 by 1 minus epsilon 1 by epsilon 1. So, plus 1 by F12 plus 1 minus epsilon 2 by epsilon 2 into A1 by A2. Otherwise, this one also. Sigma into T1 to the power of 4 minus T2 to the power of 4 by 1 minus epsilon 1 into area into epsilon 1, 1 by A1 F12, 1 minus epsilon 2 by A2 epsilon 2. So, this is the basic formula we already derived in previous class. So, based upon this formula, we discussed we derived the different rate of heat transfer between different positioning. It means rate of heat transfer between the small surface and the big enclosure. We already discussed this one also. So, similarly, rate of heat transfer between the long, it means infinite to lengthwise plates. So, it means similar plates with same area. Infinite means you can consider A1 is equal to A2 is equal to area. We already discussed this one also. So, this one is the formula for electric and analog. We already discussed this one because each surface has surface resistance and this surface also has surface resistance. So, after this one, the emitting power converted into radiosity, that is J1. Here from this surface, that is J2. So, here also space resistance is there between the radiosity 1 and radiosity 2. Already discussed this one. Okay, so two infinite parallel planes separated by very small distance. This one also we are already discussed this one. So, this one is the basic formula. Based upon this one, we can take because infinite parallel planes means the areas are same. A1 is equal to A2 is equal to A. You can consider this one. So, same areas. Next to emissivity epsilon 1 and epsilon 2. Then the final formula is equal to will be like this one. 1 by epsilon 1 minus epsilon 1 by epsilon 1 means minus 1. 1 by F12. So, we already discussed this one. So, F11 plus F12 is equal to 1. You know that because of the parallel plates. Here F11 is equal to 0. You know this one. Then automatically F12 is equal to 1. So, the value of F12 is equal to 1. 1 by epsilon 2 minus epsilon 2 by epsilon 2 is equal to 1. So, then the minus 1 plus 1 will be cancelled. Finally, the formula is equal to sigma into area T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So, this is the formula. We already derived this one. So, Q12. So, this one is just like radiation heat transfer between the two infinite parallel planes. This one already we discussed this. So now we'll see just like condition. If any shield will be placed between the two surfaces. Suppose this is the shield. Emissivity of the shield is equal to epsilon 3. Okay. Then heat transfer takes place from surface 1 to surface 3, then surface 3 to surface 2. Okay. Then we can calculate the rate of heat transfer from surface 1 to surface 2 through shield. So Q12 without shield, we know that formula. So Q12 with shield, we have to derive the formula with shield. So without shield, we know the formula. It means the heat transfer between the two parallel plates. So that is the Q12 is equal to, you know, that sigma A into T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So this one is already derived. Okay. So now we'll see if the shield is placed between the two surfaces. So next, the formula will be like this one. First of all, we consider the radiation heat transfer between the surface 1 and surface 3. Then we know the formula. If there are two surfaces, the formula will be like this one. Then rate of heat transfer from surface 1 to surface 3. So sigma A into T1 to the power of 4 minus. So shield temperature is equal to T3. Then T3 to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 3 minus 1. So this is the formula. Similarly, the heat transfer between the shield 2 and surface 2. Then we can write like this one. Q32 is equal to, the formula is equal to sigma A into, so 3 to the power of T3 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 3 plus 1 by epsilon 2 minus 1. So this is the formula. So then the final formula, it means the rate of heat transfer between the two surfaces including the shield. Then we can write like this one with the shield. So Q12 dash without shield, Q12 with shield, Q12 dash. The formula will be like this one, the final formula. So Q12 dash is equal to same. So sigma A into T1 to the power of 4 minus initial temperature minus final temperature based upon the surface resistance. Electrical analog formula based upon the electrical analog formula, we can write like this one, epsilon 3. So this one epsilon 3 and epsilon 2. So this is the formula. So you know that based upon it. We'll see just a few words regarding the shield. What is the importance of the shield? Okay. So radiation heat transfer between two surfaces can be reduced greatly by inserting a thin or low emissivity sheets. The importance of sheet is to reduce the rate of heat transfer between any two surfaces, but by inserting a thin low emissivity sheets, okay, between the two surfaces. Such highly reflective thin plates or shells are simply called a radiation shield. So the importance of the radiation shield is to reduce the heat transfer between the two surfaces. Okay. So multi-layer radiation shields also can be placed between the two surfaces. That multi-layer radiation shields constructed of about 20 sheets per thickness separated by evacuated space are commonly used as in cryogenic and space applications, just like that is the one of the application of shields. So the radiation shield finally reduce the heat transfer by effectively increasing the surface resistance. By increasing the surface resistance, automatically heat transfer will be reduced. Okay. Lower the emissivity of the shield, higher the resistance. So you can, if you just like if you consider the lower emissivity shield, automatically resistance will be increased, automatically rate of heat transfer between the two surfaces will be decreased. So this is the importance of radiation shield and the application of that one also. Okay. So this one is just like electrical analog formula. If the one shield is placed between the two surfaces, these are the two surfaces. Here one shield is placed. One shield is this one. This is the surfaces 1, surfaces 2. So here this is a shield. So this one is a shield. Then we'll see. So for first surface, it has a surface resistance, that is 1 minus epsilon 1 by A1 epsilon 1. And then so comes into picture, that is the radiosity J1. So next similarly, this surface shield also has the just like surface resistance. So that is the 1 minus epsilon 3 by epsilon 3 surface resistance. So this shield to radiosity J3. Okay. Then just space resistance we can identify between the J1 radiosity J1 and J3. So this one is means we can just write like this one. So this is the shield surface 1 and the surface 2. So here shield is there. We know that surface has the surface resistance 1 minus epsilon 1 by epsilon 1. Then radiosity. Okay. This shield also surface resistance 1 minus epsilon 3 by epsilon 3. Then radiosity J3. So here the in between J1 and J3, it means radiosity J1 and J3, there also is a space resistance, that is the 1 by A1 F13. So same situation, similar situation here also you can see. The shield has a surface resistance 1 minus epsilon 3 by epsilon 3 into area, if you consider area A. So then radiosity J3. This surface has the surface resistance. So surface resistance 1 minus epsilon 2 by epsilon 2 into area A2. You can consider. Then radiosity J2. The in between J3 and J2, there is a space resistance. It means 1 minus 1 by A2 into F32. So these are the just like surface resistance. This is the formula for electrical analog formula. So by using the electrical analog formula, we can identify the number of resistances. It means either surface resistance or the space resistance. Then we can write the formula based upon this radiation electrical analog formula. Just like Q12 is equal to, it means rate of heat transfer from surface 1 to surface 2. So EB1, emissive power of the body 1 or play surface 1 to EB2. So emissive power of the body or surface 2 by, so all surface resistances, it means this 1 by epsilon 1 by A1 into epsilon 1. So similarly just then 1 by A1 into F13. Then you have to consider all the resistance. Then you will get the final formula. It means you know that EB1 hyperintensity goes sigma into, so T1 to the power of 4. You know that here also EB2 is equal to sigma into T2 to the power of 4. If you substitute these values, we will get the final formula. So that is nothing but, so the final formula is equal to Q12 dash. Q12 dash is equal to sigma A into T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus epsilon 3 minus 1. And the final formula you can see like this one. Okay, this one. So Q12 net. So with one shield, the formula is equal to sigma A into T1 to the power of 4 minus T2 to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 3 minus 1. So plus 1 by epsilon 3 plus 1 by epsilon 2 minus 1. So this is the formula. It means the formula, this is with shield. So this is the formula for the without shield. So you can see two types of formulas here. One is the without shield. The formula is equal to sigma A into T1 to the power of 4 minus T2 to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. This is the without shield. This one is the with shield. So based upon these two formulas, we can solve few numericals based upon these two formulas. So here, if you consider just like condition, the emissivities of three surfaces, it means two surface and shield. Just like if the emissivities are same, it means epsilon 1 is equal to epsilon 2 is equal to epsilon 3. What will be the condition? Okay. When one shield is inserted between the two surfaces, the direct radiation of heat transfer between them is called, it means off. So okay. We know that radiation heat transfer between any two shields. So same, just like Q13 net is equal to Q32 net. You know that rate of heat transfer is uniform between the shields. So then the formula is like this one. So radiation shield does not deliver or remove heat from the system. So Q12 net is equal to Q32 net. So we can use this formula also. So for finding of any unknown temperature of T3 or just like radiation between the surface 1 and the shield and or surface shield to surface 2, just we can use this form. Okay. So this is the condition. If the emissivities are same, then the corresponding value T3, you can calculate this one, that the value of that one is equal to T3 to the power of 4 is equal to half of T1 to the power of 4 plus T2 to the power of 4. For the solving of numericals, you have to remember this one also. So based upon these formulas, we'll see just like few numericals, solve few numericals for proper understanding of rate of heat transfer between the two shields. If any shield is placed between the two planes, two surfaces. The first numerical, two very large parallel plates. Very large means we can consider the areas are both areas are same. So A1 is equal to A2. Okay. Emissivity is also given. Emissivity epsilon 1 is equal to 0.3. Epsilon 2 is equal to 0.8. So determine the percentage reduction. In radiative energy transfer with a polished aluminum radiation shield. So there is a one shield. The shield emissivity is equal to epsilon 3 is equal to 0.04. Is placed between them. Okay. So here just like we have to find out the percentage reduction. Percentage reduction means, so first of all you have to find out the rate of heat transfer Q12 without shield. You know the formula, that is the sigma A into T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus epsilon 2 minus 1. So this is the formula, you know this. Next to with shield. So this is the without shield. So next to formula, you know that with shield. You know the formula with shield is equal to Q12 dash. So sigma A into T1 to the power of 4 minus T2 to the power of 4. So initial and final temperatures by 1 by epsilon 1 plus 1 by epsilon 3 minus 1 plus 1 by epsilon 3 plus 1 by epsilon 2 minus 1. This is the formula. So by using these two formulas, we can find out the Q12, that is the rate of heat transfer without shield, Q12 dash rate of heat transfer with shield. Then you can find out the percentage reduction. Percentage reduction is equal to difference of these two. So Q12 minus Q12 dash by total Q12. So then into 100. Then we will get the percentage of this one. So based upon these formulas, we will solve this one. See here how to solve this numerical based upon these two formulas. It means without shield and with shield formulas. So the rate of heat transfer without shield and the rate of heat transfer with shield. So first of all, we will calculate the rate of heat transfer without shield. So it means Q12 dash here. You can observe. So this is the two plates. These are the two plates. So plate 1 and plate 2. Okay. So here without shield, emissivity of the first plate epsilon 1 is equal to 0.3. Okay. So in epsilon 2, emissivity of the plate 2 epsilon 2 is equal to 0.8. So already here given. Then you know that according to numerical, two very large parallel plates means we can consider those are the infinite means you can consider the areas are same. A1 is equal to AT is equal to area. Okay. So A1 is equal to AT is equal to area. Then we know the formula of two surfaces, just like F11 plus F12 is equal to 1. This formula. Then F11 is equal to 0, you know that one, just F12 is equal to 1. So U factor or shape factor between the two plates, two parallel plates, you know the formulas. F11 is equal to 0, F12 is equal to 0. You know the formula. So what is the formula is equal to? So Q12 is equal to sigma A. Otherwise, if you consider heat flux or Q12 by area, sigma into T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Here temperatures are not given. For the percentage, for the reduction percentage, no need of these temperatures also. Then the formula is equal to, we can write like this one. Sigma is equal to, you know, the value of 5.267 into 10 to the power of minus 8 into, so T1 to the power of 4 minus T to the power of 4. So this is the 10 to the power of minus 8. You can write like this one here. It means 1.56. 10 to the power of minus 8 can be T1 by 100 to the power of 4 minus T2 by 100 to the power of 4. Okay. 100 to the power of 4. You can convert like this one. Just like we are sending the 10 to the power of minus into in bracket. So this is the form 1 by epsilon 1. You know that epsilon 1 is equal to 1 by 0.3 plus 1 by 0.8 minus 1. Okay. If you solve this one, just we will get the values here. Just like already I have written here. Just you can observe this one. So here, just like so, Q1 is equal to sigma into T1 to the power of 4 minus T to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So you know that sigma, just we have written directly sigma T1 to the power of 4 minus T to the power of 4 by, just we are substituting what are the given data. So given data is equal to epsilon 1 and epsilon 2. So 1 by epsilon 1 is equal to 1 by 0.3, 1 by epsilon 2, 1 by 0.8 minus 1. So the value of 1 by 0.3, 1 by 0.8 minus 1, the value is equal to. So 0.279. So it means 0.279 into sigma T1 to the power of 4 minus T2 to the power of 4. So this is the values. So sigma, you know, the Stephen Boltzmann constant. No need to substitute here because we are just finding the percentage of it. So this is the value for the just like radiation heat transfer between the plates without shield. Now we'll see the radiation between the two plates with shield. With shield, you can see like this one. So one shield is placed between the two plates. So plate 1 and plate 2. This is the shield. Then you know that emissivity of the shield is equal to epsilon 3 is equal to 0.04. Remaining same, epsilon 1 given 0.3, epsilon 2 given 0.8. Areas are same, you know this one. Then F13 is equal to 1, F32 also is equal to 1, you know this one. So because F11 plus 13 is equal to 1, automatically F11 is equal to 0. Then F13 is equal to 1. Okay, then we can use the formula, that one. So rate of heat transfer between the two plates with shield, it means Q12 dash. So Q12 dash is equal to, you know, that sigma into T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus epsilon 3 minus 1 plus 1 by epsilon 3 plus 1 by epsilon 2 minus 1. This formula you can apply this here. Okay. So sigma into T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 3 minus 1 and 1 by epsilon 3 plus 1 by epsilon 2 minus 1. Okay. So if we substitute the values, it means sigma T1 to the power of 4 minus T2 to the power of 4 by the values, it means 1 by epsilon 1. So epsilon 1 value is equal to 0.3 plus epsilon 3 is equal to 0.04 minus 1. Okay. So plus 1 by epsilon 3, 1 by 0.04 plus 1 by epsilon 2 is equal to 0.8 minus 1. So if you substitute just like if you calculate these values, then we will get the just a final value. So the final value is equal to here. So that is given here. Just you can observe. So Q12 or 2. We can write like this one. This is the Q12 dash. So we can write like this one. Q12 dash. This is the Q12. Okay, you can write like this. So the value is equal to this one. So 0.0196. 19 into sigma. So here 0.279. So then the percentage, you know that the percentage is equal to difference between these two by initial value. It means Q12 dash minus Q12 minus Q12 dash by Q12. It means so sigma into T1 to the power of 4. So in numerator and denominator, that will be cancelled. The final value is like this one. So 0.279 minus 0.0195. So 0.27. So this is the value. So if you simplify this one, just you will get the final answer. The final answer is equal to like this one. So that is the percentage reduction is equal to 93.15%. So in this way, just like we can calculate the radiation values, radiation heat transfer through radiation between the two plates with shield and without shield. Okay. So we'll see one more numerator. So calculate the net radiant heat exchange per meter square. So heat flux you have to consider this one. So area is equal to 1 meter square. You can take this one. For two large parallel plates. Here also large parallel plates means we can consider area A1 is equal to A2 is equal to area. So both areas of the plates are same. Okay. So a temperature, here temperatures are also given. Temperature of the first surface. So T1 is equal to 427 degrees Celsius. So always in radiation topic, always you have to convert the temperature from degree Celsius to Kelvin, because we are using the T power 4, T to the power of 4. So 427 plus 273. So 700 Kelvin. So this is the, so temperature of the first surface is equal to 700 Kelvin. Similarly, temperature of the second surface is equal to 27 plus 273. So T2 is equal to 300 Kelvin. So these are the temperatures. Emissivity of hot plate. So first plate. If you consider this is the first plate, this is the second. Emissivity epsilon 1 is equal to 0.9. Temperature T1 is equal to 700 Kelvin. So emissivity of the cold plate. So this T2 is equal to 300 Kelvin, and emissivity T epsilon 2 is equal to 0.6. If a polished aluminum shield, so here also shield. So there is a one polished aluminum shield is placed in between them. Find the percentage reduction in the heat transfer. Emissivity of the shield. So there is a one shield. So emissivity of the shield epsilon 3 is equal to 0.4. Okay. So find the percentage reduction, heat transfer, percentage reduction. Okay. So just like here, just we have to construct this one. Also, we have to find the temperature of the shield. Also, we can calculate here. So based upon this process, follow this process. First of all, you can find out the without shield. So without shield formula, you know that sigma into area is equal to 1 meter square. You can neglect this one. Sigma into T1 to the power 4 minus T to the power 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So that is the without shield form. Okay. Epsilon 1 and epsilon. Okay. So if you substitute the values, then we will get the rate of heat transfer without shield between the two plates. The rate of heat transfer between two plates without shield. So this is the formula. Q1 is equal to sigma into area is equal to 1. T1 is power 4 minus T2 is power 4 by 1 by epsilon 1 plus epsilon 2 minus 1. Okay. So you know the value of sigma. Sigma is equal to 5.67 into 10 to the power minus 8. The conversion of 10 to the power minus 8 is like this one. 700 by 100 to the power of 4. Okay. So here 300 by 100 to the power of 4. So by you know the values of emissivity is epsilon 1 is equal to 0.9 and epsilon 2 is equal to 0.6. So the final value is equal to 7402.6 watts. So this is the value. It means the rate of heat transfer between the two plates without shield, the value is equal to like this. Then we will find the rate of heat transfer between the two plates with shield. With shield means from just a surface 1 to surface 3 and the surface 3 to surface 2. So here rate of heat transfers are same. So Q13 is equal to Q32. Okay. So rate of heat transfer does not change. You know that with shield. Okay. Rate of heat transfer from surface 1 to surface 3 Q12 is equal to rate of heat transfer from surface 3 to surface 2 Q32. Okay, you can equal that one. So like this one. You know the formula Q13. Q13 is equal to, so sigma into area you can neglect. So T1 to the power of 4 minus T3 to the power of 4 by 1 by epsilon 1 plus epsilon 3 minus 1 is equal to sigma into T3 to the power 4 minus so T2 to the power 4 by 1 by epsilon 3 plus 1 by epsilon 2 minus 1. Okay. Here both are same, Q13 and Q32, like this one. You can equal like this one. Okay. So area and the sigma will be cancelled on both sides. Then you know the values of values of temperatures. Values of temperature is equal to 700 by just like sigma means we are considering 5.67 here into 10 to the power minus it will convert into just like in brackets by 700 by 100 to the power 4. Okay, so 5.67 here, 5.67 here will be cancelled. Then 700 by 100 to the power 4 minus T3 by 100 to the power 4. Here also T3 by 100 to the power 4 minus 300 by 100 to the power 4. Here T3 by 100 to the power 4, T3 by 100 to the power 4. Just you can take this one, T3 by 100 to the power 4. The value is equal to 100 to the power 4. 100. So T3 by 100 is equal to, we can consider this is the x value. Okay. You can find out the T3 value also here. Then the value of this one is equal to 2401 minus. So we are considering this is the x to the power 4 by. So this value is equal to 1.11. This value is equal to just like 25 minus 1. Okay. So similarly, x to the power 4 because T3 by 100 is equal to x to the power 4 minus 3 by 100. 300 by 100 means 3 to the power 4, that is 81 by 1 by 0.4 means 25. 1 by 0.6 means 1.67. So then we'll get some equation. Then if you solve this one, automatically x value will be occurred. The x value is equal to like this one, just 5.95. So automatically you can find out the T3 also. So T3 is equal to, so temperature is equal to 595. 595. So by using this temperature, we can find out the rate of heat transfer between surface 1 and surface 3. So this value, you can find out the Q13. If you find out the Q13, the Q32 also same. Q13 is equal to Q32. So just like then we'll see with shield. Just we are finding the Q13 net. Another value of T1 700. T3 also we got that one. That is the 595 Kelvin. So then if you substitute the values 1 by epsilon 1 value 1 by 0.9 and epsilon 3 0.4. So if you find just like substitute the values, then we will get the Q13 net. So this is the Q13 net. Q13 net is equal to Q32 net. Both are same. You know that. Okay. Then reduction in heat flow. The reduction in heat flow due to shield. So we can write like this one. Q12 overall net minus Q13. So due to shield net is equal to 7143. So this is the value differences. So then percentage reduction is equal to just this difference by just overall net, that is the 7402.6. automatically we will get this one 96.5% reduction. So in this way also just we can find out the values of percentage reduction. Okay. We will see just one more numerical. So this one is two large plates. Two large plates are maintained at a temperature, that is the 900 Kelvin and the 500 Kelvin respectively. So each plate has a area. Area of the plate also given 6 square. Compare the net heat exchange between the plates for the following cases. So there are two types of cases. One is the both plates are black. Black means you know that emissivity are 1. Emissivity 1 is equal to emissivity 2 is equal to 1 value. So plates have emissivities. So second condition, MCT1 is equal to MCT2 is equal to 0.5. So these are the black surfaces. Black surface MCT is equal to value 1. And so next MCTs, plates have MCTs. These MCTs, second condition, MCTs of first surface and MCT of the second surface is equal to 0.5. So in this these two cases, just you have to find out the values. What is the net heat exchange between the two plates? Okay. So the first condition, MCT1 is equal to MCT2 is equal to 1 because the black body. So then you know the formula for the rate of heat transfer between the two surfaces, that is the sigma A into T1 to the power 4 minus T2 to the power 4 by 1 by epsilon 1 plus n 1 by epsilon 2 minus 1. So epsilon 1 value 1, 1, 1 minus 1 means 1. So this value is equal to 1. Then we can substitute the values of temperatures also. So temperature 900 kelvins and 500 kelvins. It means area also given 6 meters square. Okay. The area is equal to 6. Okay. So Q1 is equal to area 6 into sigma value 5.67 into 900 by 100 to the power 4 minus 500 by 100 to the power 4. So 1 by epsilon 1 is equal to 1. 1 by epsilon 2 is equal to 1. Then the values, this will be cancelled. The final value Q net, so Q1 to net for the black surfaces, both the black surfaces. So value is equal to 201.9 into 10 cube watts. So this is the case 1. Case 2 is equal to this. It means both plates are gray surfaces like this one. So epsilon 1 is equal to epsilon 2 is equal to 0.5. So similar way, just we can substitute the values of epsilon 1 and epsilon 2 in the formula. So area 6, you know that, sigma 5.67, you know that, temperatures also say 900 by 100, 500 by 100 to the power 4. So then epsilons 1 by 0.5, 1 by 0.5 minus 1. So here also if you simplify this one, you will get the value. That is the value. So in this way, different numericals you can solve based upon the these two formulas, without shield and with shield formulas, for finding the rate of heat transfer between two surfaces with shield and without shield. Okay. So like this one, just like we can solve this, solve the numerical. So one more numerical also here, just we can solve this one, just follow me. So determine the radiant heat exchanger. Radiant heat exchanger. So we have to find out the radiant heat exchanger. So between the large parallel sheet plates, large means area A1 is equal to A2 is equal to A. You can consider this one. MCT is also given, epsilon 1 is equal to 0.8 and epsilon 2 is equal to 0.5. So held at a temperatures T1 is equal to 1000 Kelvin, T2 is equal to 500 Kelvin. Okay. If a thin copper plate, so there is a shield epsilon 3 is equal to 0.1 is introduced as a radiant shield between the two plates. Okay, just like sigma value is given, you know the value because the Stephen Boltzmann constant is equal to 5.67 10 to the power minus 8 watt per meter square Kelvin to the power 4, just the values. So first of all, so radiant heat exchange means with shield, directly you can find out rate of heat transfer Q1 to net with shield. With shield means you know the formula. So that is the sigma A into T1 to the power 4 minus T2 to the power 4. Right? So with shield means 1 by epsilon 1 plus 1 by epsilon 3 minus 1, 1 by epsilon 3 plus 1 by epsilon 2 minus 1. So by using this formula, you can solve this one. So if you substitute the values, just like you can see like this one, area is equal to what is the area? Okay. So you can find out the flux Q12 by A is equal to So sigma value is equal to 5.67. 5.67. 10 to the power minus 8 means we can write like this one: 1000 by 100 to the power 4 minus 500 by 100 to the power 4. Okay, you know the epsilon 1 value is equal to 0.8, epsilon 3 is equal to 0.1. Similarly, 0.3, epsilon 2 is equal to 0.5. So if you substitute the values, then you will get the final value. That is the rate of heat transfer between the two plates with shield is equal to 2501.5 watt per meter square. So this is the flex 212 gas. So in this way, just like we can solve the different numericals. Okay, these are the just other reference books. We can refer these books to solve more numericals which are related to rate of heat transfer between the two plates. Thank you for listening to this class. So for next class, we'll see the few more numericals. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.